Hello, colleagues. I think I'm still entitled to call people from UCL colleagues. I'm Anthony Finkelstein. I was formerly Dean of Engineering at UCL, and I'm now the President of City St George's, University of London, just up the road in Clerkenwell. It's a pleasure to welcome you here to this lunchtime lecture, From Waste to Wonder, and it's a particular pleasure to welcome my friend and colleague, Professor Mohan Edirisinghe, OBE, FREng, the Bonfield Chair of Biomaterials in UCL's Department of Mechanical Engineering. He will deliver today's lunch hour lecture, From Waste to Wonder. He's one of the UK's leading materials engineers, known for his pioneering work at the intersection of manufacturing, nanotechnology, and biomedical innovation. He is the recipient of the 2023 Royal Academy of Engineering Colin Campbell Mitchell Award, and in addition, the 2024 Royal Society Clifford Patterson Medal. His research exemplifies how careful scientific insight can transform low-value or discarded materials into high-value applications with real societal benefit. Pressure spinning is an example of this. It's a fast, energy-efficient method for making tiny fibres and shapes from soft, often eco-friendly materials. Recent improvements are making it more viable and factory ready. The theme of this lecture speaks directly to the challenges of sustainability, resource efficiency, and technological ingenuity, all of which confront us across the different sectors we're interested in. I can think of no one better placed than Mohan to illuminate the possibilities. So Mohan, over to you.
Thank you very much, Sir Anthony, for your introduction, very kind words, and also for chairing this lecture. I want to keep this brief, but I like to thank all the ladies and gentlemen who are gathered to listen to this talk. I also like to thank UCL Events for inviting me. It came as a surprise. From waste to wonder, how nature's leftovers are shaping the future of green materials. And I want to thank, in particular, UCL Mechanical Engineering for giving me a very happy and productive home to carry out my research. In particular, I want to thank the UCL Mechanical Engineering Workshop. They have really helped me design, construct, and maintain the many vessels and devices that I'm going to show today. It's been a great pleasure. Many thanks, Angelo Del Buso and Peter Kelly in particular. I like to also thank my research team, too numerous to mention. I will mention some individuals as the talk goes on, but I would also like to thank my research sponsors, EPSRC in particular, several industries and several commercial organizations, and many foreign governments who have sent their scholars to work on this topic and others with extra funding. That has made me persevere and carry on. So, from waste to wonder, you talk about green materials. The green material or the material I will consider today is cellulose, but to produce cellulose, to make it green, you got to take it through the waste to wonder process, which I will explain in a minute. Now, unfortunately or fortunately, green materials don't just come up on their own. They have to be manufactured. And therefore, the manufacturing route, pressure spinning, has really enabled us to understand this. Pressure spinning, we were delighted to learn about 10 days ago, has been shortlisted for the Collaborate to Innovate Awards 2025 by the engineer. And early next year, we'll find out who's won. But it's a great honor to be shortlisted. Many individuals, as I'll mention later, have contributed to this research. It's a very simple technique where we have a rotating barrel, say, for example, a cylinder, with perforations on the circumference, and the simultaneous, and that's the key word, input of pressure and rotation causes the jets to flow out from those orifices. Many collaborators, many academic advisors, and partners. I want to thank them with the bottom of my heart, and that is so important to remember. So today's talk, in view of the global audience who are gathered, members of the public, it's our duty to bring science to the public. And therefore, I will make a kind of a broad-based lecture, not diving into anything in particular to any depth. Now, waste, in terms of this particular talk, is plant or animal dung. There are many other forms of waste, but I will, of course, dwell on a little bit on plant and then on animal, the main thing that we are going to extract the cellulose from. And then we have to convert that at least into small facets of workable materials. And that's why we make fibers, ribbons, or meshes of the material to start with. I mean, I will today raise many questions rather than answer them. That is my style. I will keep knocking at the door until it opens, is a good saying to follow. Now, to do this work, I am putting together a team, particularly with my collaborators, Edinburgh Napier University. Dong Yang Soon is one of my very first former PhD students, who was in UCL Mackenzie, where I have graduated 53 PhD students to date by primarily supervising them. Teesside, and now we have two collaborators from India, one a commercial organization. And with the shift, people who've seen this and say, can you also try horse dung? We said yes, and Stable Futures, Perry Robinson has become a very good friend, and he will be listening to this with great keenness because we like to extend it there. And then also we have HDDAES extracts from Sri Lanka who have let us say by default, good science sometimes happen by accident, into cinnamon, derived cellulose. Cinnamon gives a lot of waste, and that has to be then transformed into cellulose, as I will briefly explain. All these researchers have really started just at the starting line rather than the finish. And my colleagues at Hacettepe University in Turkey, Professor Merve Gultekinoglu in particular, have helped in the cinnamon part of the work to date, and I'm sure they will be playing a crucial part in this internationally. So to begin with, UCL, Edinburgh, and Teesside, we reviewed the subject, how to derive green cellulose, nanocellulose fibrils from waste. We published that in the International Journal of Biological Macromolecules about a year ago. And for people who are interested in this topic, please read that review. It has many other references from many other great people that we could talk about. The problem is real. It's a very big problem. Cow dung, say, for example, and these are numbers not just from the literature. I have collected them from the actual commercial partners that we have at the moment. The tonnage of these materials, which can't just be thrown into manure, is huge, and they give a big contamination problem for water. They will give a bad effect on the environment, the noxious gases, and they can be full of bacteria. So we got to deal with this problem. This is something that will affect the environment and continue to affect it. The animals are very useful to us. For example, the dairy farming industry has received a big boost by the kind of work that we are proposing and doing. Now, one of the reasons why we went into this work is because we believed that we had the solution. When Edinburgh Napier said, okay, here we are sending, they do all the processing there. We will send you a sample derived from seaweed or from cow dung nanocellulose fibrils. Can you process that? I thought, using this marvelous process developed by Yankee Dye, who was a PhD student at that time, and now Dr. Dye, who is a postdoc in another department, invented this process where she converted the basic pressurized gyrator into a nozzle pressurized gyrator. As you can see, it won the front cover of the actual journal, and also proved that you can produce these fibers with great orientation and uniformity, homogeneity in great quantities. But we were surprised when the solution was put, no fibers came out. And we have to then scratch our heads and, find out what the literature said. Cellulose, although it's a lovely material, many users, is hydrophobic. So it's not so easy to process it into usable components. So what we did, we took that, solution, and we made the vertical axis spinning gyrator into a horizontal movement one. And we were surprised because the jets that landed on a water bath did give us a very, very nice collection of fibers. Fibers, as you can see, films or ribbons, controlled basically by the viscosity of the solution. So there's a very distinct and useful concentration viscosity relationship. And that means that we can get ribbons when we want, we can get fibers when we want, we can get films when we want, when we use the right solution. And we published this in the double-digit impact factor journal, very impactful journal of cleaner production. It took a year to go through the machinations of the reviewers, but that's what you are. There's no pleasure without pain, I suppose. And then the work generated a lot of interest. It was reported by the engineer. It was reported by several outlets, including the farming community in the USA, in China, and also a podcast with a journalist from a newspaper. And that was a very, very important, precise discussion. So I would like you to listen to it.
A new technique to extract tiny cellulose strands from cow dung and turn them into manufacturing-grade cellulose has been developed by researchers from UCL, Edinburgh Napier University and Teesside University. Cellulose is found naturally in the cell walls of plants, and it was first used to create synthetic materials in the mid-19th century, including the original material used in photographic film, celluloid. You can also find cellulose in everything from cling film to surgical masks, paper products, textiles, foods, and pharmaceuticals. Even though it can be extracted organically, it is also often produced synthetically using toxic chemicals. To tell us about their new environmentally friendly pressurized spinning technique, we caught up with UCL Professor Mohan Edirisinghe in the Department for Mechanical Engineering and senior author of the study.
I, about 10 years ago, created a process called pressurized gyration, pressure spinning, which is basically a rotating vessel which has orifices on the surface or needles on the surface that can eject out jets, and has created over a dozen sister processes. And in this particular operation, we created a new process where the pressurized gyration, the pressure spinning, takes place over a horizontal axis. And that was the key, because then you can direct the jet to a water bath
which allows you the formation of the cellulose fibers. Why cow dung? It's good to clean up the environment. It's a cheap source that people are trying to get rid of. It is a process that is attractive, can be scaled up. The rotating drum can be essentially of any diameter, and therefore you can control the fibers and the yield that you get.
This is the first time that cellulose films, ribbons and fibres have been manufactured from animal dung in this way, using a scalable mass production route. And Professor Edirisinghe explained why implementing the technology would be a win-win situation for manufacturers, dairy farmers and the environment.
So the source that you use has to be sustainable. It's got to be environmentally friendly, the process of extraction if you're using any. So animal refuse or plant refuse, it's got to be cleaned up. And the cleaning up on its own, raises the question, where do you dispose it of then? But if you can get that collection of material that you want to dispose of converted into something that is economically sound, good to utilize cellulose in this instance, through a process that is also cheap and energy efficient to run, that is the way forward.
To find out more, this study is published in the Journal of Cleaner Production.
Okay, so that was the picture about, a year ago. We've not stopped there. We have converted our actual horizontal gyrator into a twin chamber unit now. So rather than rotate at the speed, pressure, and collection distance, one particular solution, we can do two. So we can do cellulose together, co-sheath, cellulose alginate. The alginate is hydrophilic. So we got a lot of combinations scientifically to actually venture forward with this. And what you're seeing now is the actual dual chamber co-sheath gyrator in action, and it deposits the fibers, and then we collect the fibers and we examine them, dry them and examine them. We get a nice crop of fibers here, and by microscopy we can prove that they are indeed co-sheath. We have a very interesting material coming up. As I told you before, working with HDDS extracts in Sri Lanka, Binod De Silva, a new PhD student who is at the very outset of the work, is going to look at microcellulose derived from cinnamon waste, and that could lead us to a much better understanding of the processes, the science and technology behind it. That's very much work at the starting point. We also have another research student, Jieshuan Ren, soon to be a doctor, I hope, marching on at a great pace, dealing with the cow dung and hopefully the horse dung problem. And they are backed up by my good friend, Dr. Mehmet Aydogdu, from time to time to put the kind of postdoctoral push into this work as well. And I hope we are building the momentum up into a very large project with substantial funding, with industrial backing. So that's the kind of state of the art at the moment. This is the key. Whether you derive the cellulose from seaweed, we published this in Cellulose in 2024, or from the cow dung or horse dung or whatever it is, this is the key scientific element. The viscosity concentration plot really shows us which way to go for which product. And what we got to do is to deal with the volumetric quantities. That is a very important thing to remember. So I'll briefly go through the process, which is basically carried out in Edinburgh Napier and sent to us. Many other people are joining in. We do, you might say, the more critical but easy process of taking the nanocellulose. Nanocellulose fibrils, as you can see, are very interesting, morphology in its own right. But it cannot be pulled into shape. And shape forming is a very, very important issue in this whole operation. So we take the nanocellulose, water washing, and homogenization, and then this is the first step of characterization. We dissolve it in what is called an ionic liquid. I want to keep that kind of proprietary at the moment because it is recyclable, but we are developing it all the time. We want to, the philosophy in my lab is to use water-based, environmentally friendly scenarios wherever possible. And wherever possible, we move on to that. We measure the surface tension and viscosity because we feel that governs the jetting. And then after the jet generation and gelation, we look at the products. And some very high volume of products has been generated in this way. And the electron microscopy, which we now thankfully have in mechanical engineering, and Luna and the others has given us so tremendous support. We can look at the actual structures and some very nice structures approaching monodispersity can be obtained by changing the variables. The pressure, the working distance, the speed is kept constant at about 10,000 RPM, and of course the concentration. The speed and all these other factors can be increased if we want to go to finer and finer materials. So in characterizing, we are very careful to do XRD and FTIR because we like to show that the cellulose we produce is type 1 cellulose, what is required in an engineering sense. And that requires a whole load of characterizations. As you go to the cow dung, it is the same kind of scenario that happens. Drying, grinding, sieving, followed by washing and centrifugation by homogenization, and then we subject it to the spinning to get the process going. And as you can see, the number of passes is a critical issue. We can homogenize the project to the product to an extent that will give us a very sensible product. And the products that we get in this kind of scenario, from starting from the cellulose nanofibrils, interesting material, but not very useful to assemble to shape. We then, X-ray and FTIR them and also measure certain other characteristics, as you can see. And then we subject it and develop this curve. And as you can see in the next picture, we can get, once again, well-defined products depending on the parameters we use. So in the future, of course, we will expand the work to cellulose alginate cellulose, kind of co-sheet scenarios, composite scenarios that could be very useful in engineering, but also to other materials. But we are going to use this as our model material until we say in about a year, that's the kind of target I've set, we understand fully the principles and have the volumetric data. How can we take effective amounts of plant waste and cow dung or horse dung and convert it into something that is green through our process? The process is very important. And it was developed by many researchers, actually 10 postdoctoral researchers and 15 PhD students. And every junction of it. So this is the very first one that you can see, 2013. The work started with 3 consecutive EPSRC grants, responsive mode, which just gave us the freedom to investigate. And different facets of work was done. The very basic process reported in macromolecular rapid communications. Then in 2015, we collaborated with Kansas University in the USA to embed smart materials on the surfaces. And then in 2017, collaborated with both China and the USA to make shape memory mats. One thing that really hit the headlines was a publication we made in 2019, this particular one, the Royal Society, Proceedings of Royal Society Engineering, where we showed, with the help of Professor Tony Harker, whom I acknowledge very much for helping this work, that we can have, if we want, pressure, rotation, and feed. The feed can be continuous to develop the fibers. And then we moved on to a series of work, and I'm going to take facets of this and explain to you how the development has taken place and probably will take place in the future. Particularly collaborating with Turkey, going on to use their bacterial characterization systems to develop this method. Now, if you're calling this a green manufacturing method, you got to be able to prove it. So you got to be able to scale up to industrial level, scale down to point of care use into a small portable device, and also show what is the energy cost in this. Are we creating energy, black hole here, or are we reducing the energy? And the work done by Dr. Mehmet Aydogdu and a few others have really taken this to making it a solar, driven system, and I'll show you that at the very end of the presentation. So I keep an eye on time because I got to leave sufficient time for some questions as well. But this work in 2025, that is, all these pieces of work, too numerous to describe, I'll describe some of them, have won the front cover status in journals, and winning them in the USA, for example, American Institute of Physics, the Royal Society, they are, very competitive places. And I like the bit of competition that's thrown up at us. So one other very satisfying thing, this is now the process, pressure spinning or pressurized gyration is used independently of us, by other countries to make products that they are beginning to, develop with a commercial view in mind. And I really, have enjoyed that experience. I'm not involved in it, that's fine. But someone else in the world, globally, I have given something that the world can exploit and probably enjoy in many areas, therapeutics, in composites, biomedical composites, and also other work that will make people probably look fashionable in the cosmetics area. So that work is going on. Many other countries, Malaysia, Indonesia, and the UAE are taking this up. They send their scholars and postdoctoral researchers to us, with the work progresses at a very happy pace when that is, implemented. So this is a piece of work that is currently going on. We are really scaling up the vessel specifications to meet industrial demands. Because just having a little turning cylinder in a laboratory is good to prove a point, but then you got to show how you actually increase this, make it into a more walking, talking, dancing kind of a vessel. And this is what UCL Mechanical Engineering Workshop, I thank them very much, are helping to do. So we change here the number of orifices. We have done work with changing the orifice height levels. We also change the number of levels, the orifices that we can operate at a time. We can combine the upper level ones with the lower level ones, and we are building a very powerful vessel that the industry has already, focused their eyes on. This is important at that end. And the basic findings of this we published very recently in Materials and Design. It's a 2024 end or 2025. I think it's a 2025 paper. And we are going further on to characterize the effect on the fibers with the orifice number increase, with the orifice height increase, the dual levels coming into play. And Ahmed Al-Nedi is doing some fascinating work. And the end aim it will be to match this, to understand the fluid dynamics of this. Professor Tony Harker is allowing us, giving us help to do this, and to make a gyrator that is both horizontal and vertical. It'll be on an axis, and the UCL Mechanical Engineering Workshop is very kindly designing this for us, where we can tilt the angle. Imagine what that can do. Go from horizontal right the way up to vertical gyration. So we are learning all these things, and I think this is something to keep an eye on. One other very important facet of work is the aerodynamics, the collection of what you're making. This is so important. And by changing the collector distance and rotating the collector, you can make some fascinating bandages. You can make some shapes, and some students really, take it to very high levels, as you can see in this picture. These are very safe, soft material, water soluble. So you got to sometimes allow people to play around a little bit, with strict supervision, of course. And the latest work is we are using cinnamon and even garlic on these fiber surfaces, because we have the core sheet system. We are loading it in the sheet, characterizing it via Hacettepe University in Turkey, and we've just started a PhD in September 2024, which I think is going great guns. It is already producing very publishable results at higher impact factor, and that is something that we like to do. So we did a project. We like to emphasize that we always use, whenever possible, natural materials. And casein was a good example. It's milk fat, basically. We did this work in collaboration with Turkey and Portugal, but we used standard polymers, which we now like to use with materials like cellulose and alginate on the core sheet. It gave very good results. The actual scientific community was very interested. The work was published in the Journal of the Royal Society Interface with input from people like Professor Shavanti Homowania-Singham, who's a very good clinician. He helped me a lot in some of the aspects, and also our friends, particularly in Turkey. So that work is going to take a different slant. We also never stop thinking about reusable face masks, because face masks are generating a problem. It's creating a huge amount of waste, and that runs into billions a year. And we need to find new ways and new structures of weaving these masks together, particularly now having the facility using environmentally friendly materials like waste-derived cellulose, say, for example. So that work will incorporate bead-on-string structures, and that work is going to go forward. It started at the very outset of the pandemic. The Royal Academy of Engineering gave us a seed corn fund to get on with this after triaging it. And it has produced publishable results using an MSc student, which is a very good asset to have. MSCs coming up with their projects and then going forward. Rui Ran Huang is at another university doing a PhD, but in very close contact. We also proved beyond any reasonable doubt that we can get the core sheet structures. This is something that has been questioned. We used the third EPSRC grant to really dwell on this and prove without any doubt by using pullable, separatable fibers that we can actually deliver these core sheet fibers. It's very important because you can have a strong core and the sheath can have the more expensive functional material. Although we encourage to use natural materials that have the antimicrobial and bacterial as well, bacterial and viral and fungal antimicrobial characteristics, we could really do with going to some other materials as well that are more pungent in destroying these for filters and bandages. And we brought the core sheath gyration. As you can see, the government of Kuwait sent one of their best researchers who got his PhD here, Dr. Hussein Al-Anesi. He brought this whole, design of a vessel to produce core sheath fibers into another level. And that work was very much appreciated by the Applied Physics Reviews, American Institute of Physics, that also awarded us the cover page of their journal and did a skylight on this. There's a skylight, which in their terms is a kind of a news flash, which really encourages the use of this method to produce core sheet materials. And I want to thank LCN Sogo Huo, who has done some of this work for us, looking at the cross sections using focused ion beam fib kind of technology and SCM. One facet of investigation that is going on very happily is the work that I do with the UCL School of Pharmacy. Professor Gareth Williams, a delightful chap to work with. The student Nanang Kosim, funded by Indonesia, and they come not only with their very dedicated and motivated experience, they also come with much funding that you can spend on equipment and materials. And we have shown how to use these core sheet structures using traditional polymers, maybe with both hydrophilic and hydrophobic, active pharmaceutical ingredients. And that work now is being translated to alginate. Our student Nanang, who's coming to the end of his PhD, is working on a final installment using the alginates. And Dr. Hamta Majd, who was a very powerful character, good research student, did all this work on garlic. In fact, went to the edge of it by developing a plaster that was able to destroy destroy bacteria and become very antibacterial, as explained in this paper. And we were invited to present it as the front cover paper for macromolecular materials and engineering, the 25-year celebration paper. So that is a good starting point for garlic. We want to extend that again with greener materials. Very recently, this week has been full of events, and the last week. We had this paper of producing hollow fibers using the pressurized gyration system. This took about 2 years to get it through the review system, but when you look at double-digit impact factors, that is the way. The Royal Academy of Engineering, in awarding the 2023 Colin Campbell Mitchell Prize, did mention a lot about our capability to produce vessels that will deliver us the right products. And this has just been accepted and will appear in Applied Physics Reviews very, very shortly. So that will be a key paper. And we want to implement that to make cellulose tubes and alginate tubes and other green materials scenarios. So our gospel now, this is the work of Dr. Aida Afshar, who finished her PhD a few years ago, is to use binary systems because we have the core sheet capability. We reviewed it. once again for the double-digit impact factor international materials reviews. We show many combinations that the world can use that will give us the core sheath effect on the fibers and patches that we produce. And also, this is the work of Alicia Kelly, who came all the way from Chicago, USA, to spend not one but 2 summers in the laboratory to use materials like cyclodextrin. We encourage these materials water only, and we can also match it with other fiber making scenarios to create super patches. I never go out of the way to criticize other methods, but of course, other methods do have a problem in actual energy scenarios. And we, through a PhD student who completed very recently, a few weeks ago, have looked at the energy scenario and the sustainability scenario, critically analyzing the pressure spinning consumptions of energy with other methods. And we did use rotary speed, pressure, concentration, mapped it with diameter, production rate, and energy. We use water-soluble polymers wherever possible to bring that effect in as well. And this work is published in Global Challenges, and this is something we want to exploit. But I think the work that I presented at the Royal Society during the Clifford Patterson lecture in April 2024, I just about showed this particular unit, a portable unit. We want to take pressurized gyration completely outside the grid, the national grid. And this was a scenario then. But now, thanks to the gigantic efforts of Mehmet combining with the workshop, Dr. Mehmet Ayadoglu has really made it into a battery-driven unit. And also, as we are going to report very soon, you can see the fibers being formed. We are going to couple mains with the solar power, that's the solar panel you see in the background, and the battery, so that we can have intermittent conditions. And if it was like the summer, the last summer we had, long-lived solar power here as well. And I was lucky to spend 2 weeks over the summer in a country that could really exploit solar power. That is the unit that we are going to bring forward. And this is it performing, using solar power only. As you can see, the very end shot will show you how it has generated fibers only with solar power. The capacity is small at the moment, but we are going to store it up and use it in a variety of ways. So I think, Sir Anthony, I have used about 40 to 45 minutes, and I must let some time for questions, particularly from the public. As I said before, I will knock at the door until it opens. I have raised more questions than actual solutions, long-drawn solutions. But perhaps that's what research is meant to do. And I thank everyone who have contributed to it, who have really participated, collaborated. In particular, the 10 postdoctoral researchers and 15 PhD students who have really developed facets of the work. I probably, have taken a back seat in them. I want to thank them very much and thank all of you for listening. Thank you very much.
Well, thank you very much indeed, Mohan, for a very interesting talk. I mean, what particularly strikes me about the account you've given is the sort of the many steps that have been necessary to evolve the science and engineering in this area. So it's been a long journey. What's the next thing in order to get to scaled industrial application? How do you envisage this actually finally making that larger step?
So we have two objectives in mind, all implemented with materials derived from waste, greener materials, as you can call it, but then it wants greener manufacturing. So one side is to scale it up, as I showed you with the work funded by the UAE government and what Ahmed Al-Naidi is doing. That is to make a large vessel that's rotatable over an axis, so we can do either horizontal or vertical, combination of holes and diameters to produce a large volume of material economically, independent of the grid. And that is probably what the industry wants. But there is also another, little niche in here. Scale it down. You got to show that you can scale up and down into a unit that you can use probably, with sufficient care with materials at home, or particularly in zones where you get cut off due to floods, or where there is, particularly some of the researchers came from Turkey, where there's a, earthquake zone, and to be ready to use scaled down portable units that will do a smaller scale production, but sufficient for the purpose required. And I think we are very near that. The other scenario, we are working towards it, but scaling up in a university kind of environment is not very easy to do. But I think there will be industrial backers, particularly if the cow dung and horse dung scenario takes up. That is a volumetric task, who will help with it. So we very much hope all those ends will be met. And the most important scenario is to make it energy efficient, independent of the grid, with greener materials, which says we need greener manufacturing.
So if I recall correctly, you'd worked previously on a fiber gun for wound care. Do you envisage that sort of thing converging with this?
Now, the fiber gun was developed with electrohydrodynamic technology. So you got to have a very high voltage electric field. It's not without its downfall. Yes, I think a pressure gun can be substituted. We haven't got there to start it. But a pressure gun, which has a rotating chamber inside, can be developed to match it. I don't criticize the electrohydrodynamic methods. Electrospinning and spraying, we are learning a lot about. There's another student, FREng Van, who works with me in the School of Pharmacy, Dr. Mariam Pariska, who is, machine learning the actual scenarios. So he's coming up with a lot of interesting things that we can hopefully learn for pressurized spinning as well. But I think electrohydrodynamics is always riddled with the high electric field. If it's left unattended, it can cause a lot of corona discharge and dangerous scenarios. But it's a question of learning to handle it. So the gun equivalent in pressure spinning, we haven't. The good thing in pressure spinning is, in the electrohydrodynamic scenario, you got to have the electric field high enough to beat the surface tension forces. Electrohydrodynamics was invented about 100 years ago, Taylor featuring in it very much. Now, with pressure spinning, you don't need that, because it's a combination of pressure and the rotation and the feed, if necessary, that gives you the actual product. So you don't need to be too worried about surface tension. And electrohydrodynamics really precludes the use of water as a solvent here, because the surface tension of water is very high. But pressure spinning doesn't depend on that. So there are lots of pros and cons, but I like to think that we can learn from each other and collaborate to come to the end point rather than knocking A or B down.
Well, oh, thank you. So we've got a question here, which opens with a compliment on your very insightful lecture. And the questioner asks, my research project is on developing food packaging from sugarcane bagasse byproduct. The main focus is honing the hydrophobic abilities of the material so that they may be impermeable to water vapor. Is this a challenge you faced? And do you think pressurized gyration for generating that sort of material could be a solution?
Yes, so I don't think you can use, hydrophilic materials kind of, at random, or for that matter, hydrophobic, because they are more difficult to process, as we learned in the case of the cellulose. Now, the power comes in joining the two together. And we've already been approached by someone who has said, can you reinforce this? Have a co-anna sheet, but reinforce it with some material, again natural, that will hold the structure together. So if you read the review that we published in Biological Macromolecules, it gives you the idea of how many, waste materials are out there to exploit if we can do a little bit of basic research and thinking. So I think the answer is not straightforward, but it is very good if we can combine that hydrophilic, hydrophobic scenario, because I think that will be very useful. It has not been able to do that before because the sheet in our instances is very thin. We can make a sheet of a few nanometers, and already someone's approached and said, can you reinforce it with nanoparticles of a particular type? So I'm very much a person, when someone poses a question, I would like to do some preliminary experiments before giving the answer. So everything is possible to me. I wouldn't say anything is impossible. That is the premise that I work on. But of course, you got to tread it, analyze it, both experimentally and numerically or modeling wise to get at the solution. I mean, we learned this amount about cellulose because we thought, oh, we can just put it in a vertical nozzle pressurized gyrator and everything will be fine. To our surprise, nothing came out of it. So we had to sort of delve into another 6 months of research. But I'm very happy to speak to the question asker and, discuss it further if that is a viable way of going forward.
Thank you. So tell me, what were the big surprises? So, I mean, this has been as I said, a long journey. What were the big sort of the things that really caught you on the hop?
Well, when pressure spinning was first invented, I was very surprised that the combination of pressure and rotation will give us this kind of feasibility of controlling the structure of a fibrous products. Fibrous products are, made out of traditional polymer, can be rather damaging to the environment and in many other ways. So we got to learn ways of accommodating materials that are more neutral and natural, particularly with the environment, very important thing. But I found that very challenging on how to adapt it to use those materials. And also, when the researchers from Kansas University came along and said, here we have some peptides, we want to put it on the surface of the fiber, what do you do? So we got, thinking there. And also, there was an instance where people came up and said, right, we want to make actual products. As you saw, I showed you 3 products that are being developed by someone else, independently. And particularly the, products they are making for therapeutics, are very, very interesting. And also cosmetics is an area that we have hardly dived in. I mean, there is a person currently who has come from Turkey working in my lab, funded by TÜBİTAK, who is looking at a particular set with, making a little bit of progress on cosmetics. So every one of those cover pages did shock the editors as well as ourselves, and that is why probably it got there. So we published about 100 papers on this. 20 of those have kind of hit the ceiling, if you like to say that, winning the cover page. And that's been a great satisfaction, not only for me, but for the 15 PhD students who have worked in this area. So every one of those notions there is a surprise, is a good thing. But I look forward to more. It will never stop. We had the pandemic recently. We learned that always science wins. So that's why I never produce any conclusions at a talk given by me. Conclude is not in my dictionary. Probably, conclusions, when they come, science always alters that and sends you in another way. So each one of those 20 facets I would figure out in answer to your question as a challenge that I have put right.
Well, firstly, let me assure listeners to this webinar that conclusion is in my dictionary, so the webinar will unfortunately finish. But I've got one sort of last question that I would be interested in, which is, so what do you see? You've ploughed this particular angle highly productively, but what's your feeling about what's the next big frontier for green materials production? What do you see as the big outstanding challenge that the area faces?
Yeah, the outstanding challenge is understanding the volumetrics of this. When we dived into, animal refuse, cow dung and horse dung, we never admired this kind of scale. We thought these people were, talking something, that is very far-fetched. But there is a volumetric problem, and that has to be assessed very carefully, in line with the process that is used to generate the nanocellulose fibres, if you want to look at that, and then that taken into the process. How much conversion do we get? How long do we have to operate to get a reasonable conversion? Because the milk producing industries are really riddled with this problem. They want the volumetrics taken care of. And we got to show in the process that we can handle that amount of volume. And I'm sure there'll be lots of other researchers joining this in various parts of the world now that, we have sent out PhD students. They are forming their own groups and going forward. And I think, they will catch on to this, because most of the work, in line with the, EPSRC kind of doctrine, we publish open access. So that people can read and can transform. So that's my answer. I'm sorry if it's a bit incomplete, but I don't know the answer myself, and I'm not shy to say that.
No,
the full answer.
Mohan, I'd like to thank you for a really interesting interesting lecture. And I think personally, when I'm reflecting on the lecture and on the work you report, which I will own is not in my particular area of expertise, what I find is really interesting is the pattern of engineering innovation that it embodies, and the commitment to seeing this area of technology through, and the different dimensions and the progress that's been made. So with that, I'd like to thank you. I'd like to thank the UCL events team that have organized it, and to bring this event to a close.
Thank you very much. Thank you all.